Today's hybrid cars usually take a different approach. They connect both a gasoline engine and electric motors to the drivetrain. In some vehicles, such as the Toyota Prius, the electric motors assist the gasoline engine, where in others, the gasoline engines assist the electric motors. In most cases, the gasoline engine shuts down when the vehicle stops. In city driving, a hybrid vehicle takes advantage of engine shutdown, electric motors, regenerative braking to achieve fuel efficiencies of 30% greater than the same vehicle equipped with only a gasoline engine. Efficiency gains of hybrids are far more modest under highway driving, where they depend heavily on their gasoline engines. Most automobile manufacturers have developed prototypes of diesel-electric hybrid vehicles that achieve substantial improvements in fuel efficiency. A number of them have attained 70 miles per gallon or better. The main impediment to such propulsion systems is cost. A diesel engine plus electric drive system adds over $5,000 to the purchase price of a vehicle equipped with a gasoline engine. At current gasoline prices, an owner would not recover the additional capital costs over the life of the vehicle. Most modern engines, as discussed in a previous video segment, have the flexibility to combust mixtures containing biofuels. Biofuels are those produced from living materials and include bioethanol, biomethane, and biodiesel. The energy in biofuels originally derives from photosynthesis, which combines carbon dioxide and water and light to generate carbohydrates and oxygen. Bioethanol is produced through the fermentation of carbohydrates such as glucose into ethanol. Combustion of ethanol yields carbon dioxide plus water and chemical energy. Summing these reactions together yields a simple energy conversion. Light, solar electromagnetic radiation, yields chemical energy. In theory, the chemical energy in bioethanol propels a vehicle without any net production of greenhouse gases. Biofuels in practice are not even close to being neutral with respect to greenhouse gases because their production and use deviate significantly from 100% efficiency. Inefficiencies arise during production of biomass, transport of biomass to processing facilities, conversion of biomass to biofuels, distribution of biofuels, and combustion of biofuels in vehicles. In the following, we present the influence of biofuels of greenhouse gas emissions during production and processing. Estimates of greenhouse gas emissions during the production of biomass for biofuels often differ. The greatest expense in growing plants for human use is arable land. Therefore, the profitability of biomass production depends on yields, the economic productivity per unit land area. This promotes the use of high-input agriculture that employs sophisticated farm machinery, adequate amounts of fertilizer, pesticides, and water, and new cultivars bred for high yields under adequate agricultural inputs. Grain yields in the United States have doubled during the past 30 years, an increase attributable in equal measure to better agricultural practices and improved genotypes. Application of nitrogen fertilizer dramatically enhances crop yields, but manufacture, distribution, and application of nitrogen fertilizer contributes to the majority of greenhouse gases emitted during biomass production. A large portion of these greenhouse gases derive from the power demands of industrial nitrogen fixation, the extremely energy-intensive process that makes ammoniacal nitrogen out of thin air. Moreover, nitrogen fertilization stimulates soil microorganisms that transform soil nitrogen into nitrous oxide, a potent greenhouse gas. Crop nitrogen use efficiency has almost doubled over the last 50 years. As a result, grain yields in the United States over the last 30 years have required little additional nitrogen fertilizer and have generated little additional greenhouse gases.